On a clear autumn night, Andromeda can be seen without a telescope. It appears as a soft silver blur suspended in the dark, so quiet and faint that it almost feels close, as if some future humanity might one day reach it. After all, we call it our nearest galactic neighbor, the galaxy next door. But that phrase hides something almost impossible to hold in the mind. The light touching your eye tonight left Andromeda 2.5 million years ago, when our ancestors were still shaping stone tools on the African savanna. And light is the fastest thing the universe allows. Even at that speed, the trip takes longer than our species has existed. This is not just a very large distance. It is a barrier. A stretch of emptiness so immense that the word journey almost stops meaning anything. For most of human history, that pale patch in the sky was only a mystery with a name. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi became the first known person to record it in writing. In his book of fixed stars, he described it as a small cloud. He had no way to know what he was really seeing. No one did. For almost 1,000 years after that, Andromeda was listed beside real gas clouds and star-forming regions inside our own galaxy. It was treated as something nearby, something belonging to the Milky Way, something interesting but not extraordinary. In the late 1700s, the French astronomer Charles Messier, who spent his career searching for comets, placed it as the 31st object in his catalog. His list was made up of things that looked like comets, but were not comets. They were distractions, nuisances, objects he wanted to mark down so he would not waste time on them again. Messier 31 became Andromeda's official designation, a thing to avoid. The irony is almost painful, because the faint blur Messier filed away as an inconvenience turned out to be one of the most important objects in the history of astronomy. For centuries, the assumption seemed obvious. The Milky Way was everything. Every star, every glowing cloud, every patch of light in the night sky was thought to belong to one vast system. Beyond that system, people imagined only endless darkness. The spiral nebulae, those graceful pinwheel shapes that appeared through stronger and stronger telescopes, were believed to be clouds of gas inside the Milky Way. Maybe they were places where new stars were being born. Andromeda was seen as the brightest and largest of them. Beautiful, yes, but still local. A feature inside our galaxy, not a galaxy of its own. That belief became so accepted that it hardened into certainty. The universe was the Milky Way, and the Milky Way was the universe. For a long time, no one had the tools to prove otherwise. Then, on the evening of April 26, 1920, a quiet tension among astronomers finally came into the open. In an auditorium at the Smithsonian Museum of Natural History in Washington, two astronomers stood before an audience and argued over the size of the universe itself. It became known as the Great Debate, and it was not just a polite academic discussion. On one side was Harlow Shapley, a young and ambitious astronomer from Mount Wilson Observatory. He defended the common view. The Milky Way, he argued, was enormous, much larger than earlier estimates had suggested. The spiral nebulae, including Andromeda, were only small features inside it. They might be gas clouds or regions of new star formation, but they were local. They belonged to our system. On the other side was Heber Curtis, an older and more cautious astronomer from Lick Observatory. He argued the opposite. The spiral nebulae were not inside the Milky Way at all. They were island universes, entire galaxies in their own right. Each one was a vast, independent structure containing billions of stars, separated from us by unimaginable distances. In that picture, The Milky Way was not the whole universe. It was only one galaxy among many. Curtis had noticed something important. Novae, stellar explosions seen in Andromeda, appeared much dimmer than similar novae elsewhere in the sky. If they were the same kind of event, then the difference in brightness had one clear explanation: distance. Enormous distance. He had also seen dark lanes cutting across the spiral nebulae. They looked like dust structures in galaxies viewed from the side. The clues all seemed to point outward, beyond the Milky Way. But clues are not proof. Neither man clearly won that night. Shapley had greatly overestimated the size of the Milky Way, which made it easier for him to argue that the spiral nebulae could fit inside it. Curtis was closer to the truth. The nebulae were beyond our galaxy. But his distance estimates were rough, and much of his evidence was indirect. The audience left uncertain. The question remained unsettled. Still, that evening mattered. It captured the last moment in history when a serious astronomer could still argue that the universe was small. Before 1920, it was scientifically respectable to claim that everything in existence fit inside one galaxy. After what came next, that idea was gone forever. 5 years later, Edwin Hubble ended the debate. In 1925, using the 100-inch Hooker telescope at Mount Wilson, the most powerful telescope on Earth at the time, Hubble did what no one had done before. He resolved individual stars inside Andromeda. Not just any stars. He identified Cepheid variables, stars that brighten and dim in a steady, predictable rhythm. A few years earlier, Henrietta Leavitt had discovered something crucial about Cepheids. Their pulsation rate is tied directly to their true brightness. The slower the pulse, the brighter the star really is. So if you measure how quickly a Cepheid pulses, you can know its actual luminosity. Then, by comparing that true brightness with how faint it looks from Earth, you can calculate its distance with real precision. Hubble measured Cepheids in Andromeda, and the result was staggering. Andromeda was not a cloud inside the Milky Way. It was not a nearby feature of our own galaxy. It was a separate system entirely, floating in space at a distance so far beyond anything previously imagined that one calculation made every old map of the cosmos obsolete. The universe did not end at the edge of the Milky Way. The Milky Way was one galaxy among what would eventually be counted in the trillions. And Andromeda was the first proof. That discovery did more than enlarge the map. It changed humanity's understanding of its place in the universe forever. In a single step, the known cosmos jumped from one galaxy to at least two. And after that, the question was no longer whether other galaxies existed. The question was how many. As telescopes improved, the answer kept growing. Millions, billions, 2 trillion. That expansion of the known universe began with Andromeda. It was the first crack in the door, the first glimpse of the true scale beyond our galaxy. And that scale is almost impossible to comprehend. Before we can feel the distance to Andromeda, we have to understand what we are looking at. Andromeda is not a star. It is not a cloud of gas. It is a structure of nearly unimaginable size. And once its size becomes real, the distance to it becomes even harder to accept. Andromeda is a spiral galaxy, not a loose swarm of stars drifting together, but an organized system. It is a flat rotating disk built around a dense central region, with long curved arms winding outward from the middle. More specifically, it is a barred spiral galaxy. Its core is not simply a round concentration of stars. It has an elongated bar-shaped structure, and the spiral arms stretch from the ends of that bar like streams of water flung from a spinning wheel. From edge to edge, Andromeda spans roughly 200,000 light-years. In the simplest terms, if you could travel at the speed of light, the fastest speed allowed by the universe, it would take 200,000 years just to cross Andromeda from one side to the other. Not 200,000 miles, 200,000 years at light speed. Just across one galaxy. Inside that enormous span, around 1 trillion stars burn, 1 trillion individual suns. Each one is a nuclear furnace turning hydrogen into energy, and each one may have its own system of planets. Some of those stars are young, hot, and blue-white, shining in the spiral arms where new stars are still forming. Others are ancient red giants, swollen and cooling after billions of years of burning. Most are quiet red dwarfs, dim and small, but incredibly long-lived. Many of them will still be shining long after our own sun has gone dark. At the center of Andromeda sits a supermassive black hole. Its mass is somewhere between 100 million and 200 million times the mass of our sun. For comparison, the black hole at the center of the Milky Way, Sagittarius A star, is about 4 million solar masses. Andromeda's central black hole is between 25 and 50 times more massive than ours. It is one of the largest black holes in our region of the universe, and it anchors Andromeda's gravitational heart. Andromeda is not alone either. It has its own gravitational family, smaller satellite galaxies orbiting around it, much as moons orbit a planet. The best known are Messier 32 and Messier 110, two dwarf elliptical galaxies visible through small telescopes. Beyond them, astronomers have cataloged many smaller and fainter companions, and new ones are still being discovered. In April 2026, astronomers confirmed Andromeda 36, a newly identified ultra-faint dwarf galaxy orbiting Andromeda at a distance of roughly 388,000 light-years from its center. It was first noticed not by a professional astronomer searching through data, but by an amateur examining survey images. An entire galaxy, small though it is, had been hiding in plain sight until someone looked carefully enough. Together, Andromeda and the Milky Way are the two dominant members of what astronomers call the local group. This is a gravitational family of about 100 known galaxies spread across a region roughly 10 million light-years wide. Most of those galaxies are small dwarf systems, faint and dim, with anywhere from a few million to a few billion stars. The Milky Way and Andromeda are the giants. They contain most of the local group's mass. In gravitational terms, nearly everything else is a satellite of one or the other. Andromeda is especially valuable because it gives astronomers something we can never get from our own galaxy. We are trapped inside the Milky Way, located in one of its outer spiral arms. Dust and gas block our view in many directions along the galactic plane. We have never seen the Milky Way from the outside. We cannot. Andromeda gives us the next best thing. A galaxy similar in size and structure, close enough to study in detail, but far enough away for us to see it as a complete system. In January 2025, the Hubble Space Telescope completed the most ambitious portrait of Andromeda ever attempted. Astronomers combined more than 600 overlapping observations taken over a decade. The project required more than 1,000 Hubble orbits and produced a panoramic image of Andromeda's disk at a resolution of 2 billion pixels. Within that image, more than 200 million individual stars were resolved. Each was identified, cataloged, and studied as its own object. 200 million suns, individually pinpointed in a galaxy 2.5 million light-years away. And even that is only a fraction of what is really there. Hubble can detect only stars brighter than our sun at that distance. The hundreds of billions of dim red dwarfs and faint stellar remnants that make up much of Andromeda's population are too weak to resolve. So the most detailed image ever made of another galaxy is still, in a very real sense, incomplete. By studying the ages and chemical compositions of star populations across Andromeda's disk, astronomers also know that the galaxy has had a violent past. Roughly 2 billion years ago, Andromeda collided and merged with another large galaxy. That event reshaped its structure, triggered huge waves of new star formation, and left scars that are still visible in the way its stars are distributed today. Andromeda is not untouched or pristine. It is a survivor, a galaxy that has already passed through a major merger and emerged as the system we see now. All of this belongs to the galaxy we call our neighbor. The trillion stars, the supermassive black hole, the satellite galaxies, the ancient collision history, the 2 billion pixel portrait. And that neighbor sits 2.5 million light-years away. The more detailed and real Andromeda becomes, the more brutally the distance announces itself. Every star in that Hubble mosaic, every curve of its spiral arms, every feature we can name, is separated from us by a gap we still have not truly faced. To understand the distance to Andromeda, you cannot begin with the number itself. The human mind does not work that way. 2.5 million light-years is too abstract. It has no connection to ordinary experience. The only way to feel it is to build toward it. Start with something familiar, then move outward step by step, until the steps themselves become impossible to imagine. Begin with the moon, the closest major object in the sky, and the only world beyond Earth where human beings have physically stood. The moon is about 239,000 miles away. Light crosses that distance in about 1 1/3 seconds. The Apollo astronauts made the trip in about 3 days. By human standards, the moon is close. It is reachable. We have been there 6 times, now moved to the sun, about 93 million miles away. Light takes 8 minutes and 20 seconds to travel from the sun to Earth. A car driving at highway speed would need around 170 years to get there. We have never sent people to the sun, but we have sent probes close to it. The Parker Solar Probe has swept within a few million miles of the sun's surface. At its closest approach, it became the fastest object humanity has ever built, reaching around 430,000 miles per hour. Remember that speed. It matters later. Keep going outward. Mars, at its closest approach to Earth, is about 34 million miles away. Our fastest rovers take around 7 months to reach it. Jupiter, at its nearest, is about 365 million miles from Earth. The Juno spacecraft reached speeds above 165,000 miles per hour during orbital insertion and still took 5 years to arrive. Saturn is roughly 746 million miles away at closest approach. Cassini took almost 7 years to get there. Now reach for the edge of the solar system. The Oort cloud, a vast diffuse shell of icy bodies marking the outer reach of the sun's gravitational influence, is estimated to extend about 1.5 light-years from the sun. No human spacecraft has come close to reaching it. Voyager 1, launched in 1977, is the most distant human-made object ever built. It has been traveling for nearly 50 years. In that time, it has crossed about 15 billion miles. That sounds enormous, but it is only a little more than 0.1% of the distance to the outer edge of the Oort cloud. 50 years of non-stop flight, and we have not even truly left the backyard of our solar system. And yet the solar system is tiny compared with what comes next. The nearest star to the sun is Proxima Centauri, part of the Alpha Centauri system. It lies about 4.25 light-years away. Light, moving at 186,000 miles per second, takes 4 years and 3 months to cross that distance. That is not a travel estimate based on current technology. That is the physical minimum. Nothing can move faster than light. 4 years and 3 months is the absolute shortest possible crossing time, no matter what kind of spacecraft you imagine. Now make that more tangible. Voyager 1, moving at about 38,000 miles per hour, would need roughly 73,000 years to reach Proxima Centauri, if it were even headed that way, which it is not. 73,000 years, all of recorded human civilization, every empire and every war, covers roughly 5,000 years. Voyager would need about 14 times that entire span just to reach the nearest star. What about our fastest spacecraft? If the Parker Solar Probe, at its peak speed of 430,000 miles per hour, were aimed at Proxima Centauri, it would still need about 6,600 years to arrive. That is roughly the amount of time separating us from the earliest known copper smelting in the ancient Near East, from an era before writing had been invented. Our fastest machine, flying without stopping, would need the full length of recorded history to reach a star visible to the naked eye on a clear night. And Proxima Centauri is the best possible case. It is the closest star. Every other star in the galaxy is farther away. Most are far farther. Now step back and look at the Milky Way itself. The disk of our galaxy spans about 100,000 light-years. Light needs 100,000 years to travel from one side to the other. At the Parker Solar Probe's highest speed, crossing the full width of the Milky Way would take about 156 million years. That is longer than the time separating us from the late Jurassic period, when dinosaurs dominated the continents and the first birds were only beginning to evolve. At the fastest speed humanity has ever achieved, crossing our own galaxy would take so long that the species that launched the spacecraft would almost certainly be unrecognizable or gone long before arrival. Now, the ladder breaks. Andromeda is about 2.5 million light-years away. The Milky Way is about 100,000 light-years across. That means the distance to Andromeda is 25 times the diameter of our entire galaxy. Imagine placing 25 Milky Ways end to end, each one 100,000 light-years wide, each one containing hundreds of billions of stars. The gap between us and Andromeda is wider than all of them combined. At the Parker Solar Probe's peak speed, reaching Andromeda would take about 4 billion years. Earth itself is only 4.5 billion years old. If that probe had launched at the moment our planet solidified from primordial rock and gas, it would still be traveling today, with hundreds of millions of years left before arrival. Every mass extinction, every ice age, every evolutionary step from the first fish to the first humans would have happened during the trip, and the spacecraft still would not be there. That is the ladder. Each rung does not merely add distance. It multiplies it violently until the numbers stop feeling like numbers at all. And at the top of that ladder, separated from us by 25 galactic widths of near-perfect emptiness, is the galaxy we call our nearest neighbor. Numbers lose their force when they become too large. The human brain evolved for quantities it could see and touch. Berries in a hand, wolves in a pack, the distance to a river. Beyond a certain point, numbers drift loose from reality. 2.5 million light-years is one of those numbers. You can say it, you can write it, right? But you cannot feel it. So stop treating it as a number. Turn it into time. Time is something every human understands. Birthdays, funerals, seasons, heartbeats. Time is what you have been spending since the moment you were born. And when the distance to Andromeda becomes time, it stops being abstract. Every photon arriving from Andromeda tonight left that galaxy 2.5 million years ago. Not 2.5 million miles away. 2.5 million years ago. That light has crossed the intergalactic void at the only speed the universe permits. It has not stopped. It has not slowed. It has moved every second of every day since before our species existed. And tonight, it arrived on your retina while you looked up. 2.5 million years ago, the genus Homo had only just appeared on Earth. The earliest members of our lineage were learning to chip crude stone tools from river stones on the African savanna. There were no cities, no languages, no deliberate use of fire, no understanding of stars. The light left Andromeda at the same moment in deep time, when the first beings that could arguably be called human were taking their first uncertain steps as a lineage. And that light reached us only now, after all of human history unfolded beneath it. Walk backward through that journey. 500 years ago, the Renaissance was reshaping Europe. Columbus had recently crossed the Atlantic. The light from Andromeda was already ancient beyond measure, but it still had 500 years left to travel. 2,000 years ago, the Roman Empire stretched across the Mediterranean. The light kept coming. 10,000 years ago, the last ice age was ending. Agriculture was being invented. The first permanent settlements were appearing. The light had already traveled for 2,490,000 years and still had 10,000 years to go. 50,000 years ago, modern humans were painting caves in Europe, crossing seas and moving into new continents. The light had 2,450,000 years behind it, with 50,000 still ahead. A rounding error. A footnote at the end of a very long sentence. 300,000 years ago, the earliest known Homo sapiens appeared in the fossil record in North Africa. That is roughly the full span of our species. And by then, the light from Andromeda had already been traveling for 2,200,000 years. We are not even a footnote in that journey. We are a sentence near the end of a book that has been writing itself for millions of years. And 2.5 million years ago, when that light began its trip, Earth looked nothing like it does now. The planet was entering a deep cooling period. Ice sheets were beginning to advance across the northern hemisphere. Mastodons roamed North America. Giant ground sloths the size of elephants fed in South American forests. Saber-toothed cats hunted across grasslands stretching from what is now Texas to Patagonia. The Isthmus of Panama had recently closed, connecting North and South America and triggering one of the largest migrations of land animals in geological history. That light departed during a world that would look like a nature documentary set on another planet. It was a world filled with creatures that would never live to see the species that would one day build telescopes. That is what 2.5 million years contains. Not an abstraction, not a big number on a page, a biological epic. A span long enough for evolution to carry a lineage from rough stone tools to instruments capable of studying galaxies. Now consider something simpler than travel. Communication. Suppose you wanted to send a message to Andromeda, not a spacecraft, just a signal. You encode it, aim it at Andromeda, and transmit it at light speed. 2.5 million years later, it arrives. Whatever is there receives it, creates a reply, and sends it back. Another 2.5 million years pass. Total time for one exchange, 5 million years. 5 million years ago, our ancestors had only recently split from the lineage that led to chimpanzees. They were early hominins, creatures somewhere between ape and human, walking upright some of the time and climbing trees the rest. If a civilization had somehow existed then and sent a greeting to Andromeda, a reply arriving today would reach a planet whose inhabitants share no language, no culture, no memory, and arguably no species identity with the ones who sent the first message. The civilization that began the conversation would be as alien to the civilization receiving the answer as any creature from the deep fossil record. Communication with Andromeda is not merely impractical. It breaks the idea of conversation. The time scale destroys it, because nothing on either end can persist long enough to take part in both halves of the exchange. That is what raw distance fails to show. When you say 2.5 million light-years, it sounds like geometry, a measurement. But when you turn it into time, it becomes a fact about mortality, about how brief we are compared with the spaces between the structures we inhabit. The distance to Andromeda is not a wall we might climb with enough technology. It is a wall made of time itself, and it is older than our entire species. We have measured the distance in numbers and in years, but there is another part of it that neither one fully captures. It is not only how far Andromeda is, it is what lies between us and it. The space separating the Milky Way from Andromeda is not empty in the way space between cities is empty. It is not even empty in the way space between stars is empty. It is a different kind of emptiness altogether, with no real comparison in human experience. Start inside our galaxy. The space between stars in the Milky Way is already extremely thin. The interstellar medium contains roughly 1 atom per cubic centimeter. 1 atom in a volume about the size of a sugar cube. That is a vacuum far more perfect than anything made in a laboratory on Earth. And yet, compared with the space between galaxies, the inside of the Milky Way is almost crowded. The intergalactic medium between us and Andromeda contains about 1 to 10 atoms per cubic meter. Imagine a volume about the size of a washing machine, holding, on average, a single atom. That is about 1,000,000 times emptier than the already near-perfect vacuum between stars. It is emptier than any vacuum chamber built by human hands. The best ultra-high vacuum equipment on Earth still contains around 100 atoms per cubic centimeter, which is tens of millions of times denser than the void between the Milky Way and Andromeda. The space between us and Andromeda is among the most perfect natural vacuums we know, surpassed only by the even emptier regions deep inside the great cosmic voids between galaxy clusters. It is not just an absence of matter. It is an absence of almost everything that makes space navigable or meaningful. No stars to steer by. Inside the Milky Way, even in sparse outer regions, another star appears every few light-years. Stars become landmarks, reference points, evidence that you are traveling through a populated place. Between galaxies, there are none. You could travel hundreds of thousands of light-years in any direction and never pass near the gravitational reach of a single star. No gas clouds would mark your progress, no dust lanes, no strong magnetic field, no radiation pressure, no structure. If you were placed halfway between the Milky Way and Andromeda, both galaxies would appear as faint smudges of light, one in each direction. Everywhere else would be nothing, absolute nothing, stretching for more than 1,000,000 light-years around you. Even the idea of location would begin to lose meaning. There would be no landmarks, no visible measure of progress, except the almost imperceptible change in the apparent size of 2 distant glows over thousands of years. There are a few exceptions scattered through that void. The local group contains many small dwarf galaxies in the space between the Milky Way and Andromeda. Some orbit the Milky Way, like the large and small Magellanic Clouds. Others orbit Andromeda. A few drift somewhere between the two, loosely bound to the larger system, but not clearly belonging to either giant. These dwarf systems are real galaxies, with anywhere from a few million to a few billion stars. But compared with the emptiness they inhabit, they are like flecks of foam on a dark ocean. They do not break the void. They reveal how enormous it is. Now imagine actually traveling through it. Not the time required. We have already faced that. Think about the experience. A spacecraft leaving the outer edge of the Milky Way and entering intergalactic space would leave everything behind. Every star, every nebula, every faint glow of galactic structure. After a distance that is small in cosmic terms, the Milky Way behind you would shrink into a disk of light, then into a blur. Eventually, it would look much like Andromeda looks from Earth tonight. A faint, distant glow marking where home is, and offering nothing else. Ahead, Andromeda would do the same in reverse. It would grow over millions of years, but so slowly that no human lifetime, or even 1,000 human lifetimes, would notice the change. The crossing would not feel like motion. It would feel like stillness inside a void so complete that the word isolation is not strong enough. One faint light behind, one faint light ahead, and between them, nothing. For 2.5 million light years, nothing. There is no rescue in that space, no resupply, no way to turn back and return home in any meaningful time. No other civilization, if one exists somewhere in that darkness, close enough to matter. Once a spacecraft entered the intergalactic medium, it would be more alone than anything in human experience has ever been, or ever could be. The nearest gravitationally significant object in any direction would be an entire galaxy. And this emptiness is not temporary. It is not a gap that will fill in as the universe grows older. The universe is expanding, and that expansion is accelerating. The void between galaxies is growing. Every day, the intergalactic space between us and distant galaxies stretches a little farther. The isolation is not fixed. It is worsening. Inside the local group, gravity still holds. The Milky Way and Andromeda are bound together, and they are actually moving toward each other at about 110 kilometers per second. But beyond the local group, other galaxies are being carried away from us by the expansion of space itself. The farther away they are, the faster they recede. Galaxies beyond a certain distance are already moving away from us faster than light can cross the gap. Not because they are breaking the speed limit through space, but because the space between us and them is stretching faster than any signal can travel through it. That means those galaxies are already unreachable, not just practically, but in principle. Light we send toward them will never arrive. Light they send toward us will never reach us. They have crossed a boundary defined not by a wall, but by the geometry of expanding space. And every day, more galaxies cross that boundary. The universe is not opening as it ages. It is closing. More and more of the cosmos is being sealed away, beyond our gravitational neighborhood, one galaxy at a time. The void between us and Andromeda is not the worst of it. It is only the beginning. Now we have built the ladder. We have felt the distance as a number, as time, and as emptiness. So we reach the question behind all of this. Not simply, how far is Andromeda? We know that now. The real question is, what does that distance mean? What does it tell us about the universe we live in and about our place inside it? The true revelation is not Andromeda itself. It is what Andromeda's distance says about everything else. Andromeda is not unusually remote. It is not sitting at the far edge of what might be reachable. It is the closest major galaxy, the best case, the minimum. Every other large galaxy is farther away. Most are vastly farther away. If even the nearest major galaxy lies behind a barrier that would take 4 billion years to cross at the fastest speed humanity has ever achieved. What does that say about the rest? The next comparable galaxies beyond Andromeda, such as Centaurus A and Messier 81, lie roughly 12 to 14 million light-years away. That is 5 to 6 times farther than Andromeda. The Virgo cluster, the nearest major galaxy cluster, contains more than 1,300 galaxies and is about 54 million light-years away. The observable universe stretches 93 billion light-years from edge to edge and contains an estimated 2 trillion galaxies. 2 trillion. And the nearest major one already requires 4 billion years of travel at our fastest speed. The rest of the cosmos is not merely unreachable. It belongs to a different category of impossibility. There is a mythology around space exploration. Science fiction, visions of humanity among the stars, dreams of future expansion all tend to carry the same assumption. Distance is a problem to solve. With enough time, enough intelligence, enough technology, the universe opens. Stars become destinations. Galaxies become territories. Humanity spreads outward, and the cosmos becomes a place we inhabit instead of merely observe. Inside the solar system, that mythology can survive. We have walked on the moon. We have driven robots across Mars. We have sent probes to the edge of our planetary neighborhood. Distance within the solar system is an engineering problem. Difficult, expensive, slow, but not impossible in principle. So the mythology keeps breathing, and we carry it with us as we look beyond. But the distance to Andromeda does not merely challenge that mythology. It does not push it to its limits. It destroys it. Because the distance to Andromeda is not an engineering problem. It is a statement written into the geometry of the universe, enforced by the speed of light and the scale of intergalactic space. And that statement is clear. No physical object, obeying the laws of physics as we understand them, can cross to another major galaxy within any time frame that preserves the identity or continuity of the civilization that launched it. Even generous physics does not save the idea. Suppose a spacecraft could somehow travel at 10% of the speed of light. That is an extreme velocity, far beyond any serious crude engineering proposal, because the energy requirements would be staggering, and even a tiny dust grain hitting at that speed would strike with explosive force. At 10% of light speed, the journey to Andromeda would still take 25 million years. The entire evolutionary span from the earliest ape-like ancestors of humans to the present fits inside that travel time. Whatever launched the spacecraft would be unrecognizable when it arrived, if the concept of it still existed at all. And here is the detail that makes the conclusion final. Andromeda is moving toward us. The Milky Way and Andromeda are gravitationally bound, closing the gap at about 110 kilometers per second. Whether the result is a direct collision and merger, or a series of gravitational passes over tens of billions of years, the models agree on the scale of time. It is measured in billions of years. Two galaxies are approaching each other at hundreds of thousands of miles per hour, and gravity still needs longer than the current age of Earth to bring them together. The gap is that large. When the merger finally happens, and current models suggest it most likely will within the next 5 to 10 billion years, it will not be a journey. No one will travel from here to there. No spacecraft will cross the void. The galaxies will simply fall together under gravity, like water flowing downhill, mindlessly and impersonally, across a time span so vast that no conscious being could experience more than the smallest fraction of it. The distance that no traveler can cross will be erased by the universe itself, because the universe has billions of years and no impatience. What remains after that merger will become our permanent home, one large elliptical galaxy formed from the remnants of the Milky Way and Andromeda. It will be the last major gravitational gathering in our corner of the cosmos, because beyond the local group, dark energy is winning. Every other galaxy is being carried away from us by the expansion of space, and that motion is accelerating. In roughly 100 billion years, every galaxy outside our local group will have receded beyond the observable horizon. Future astronomers, if any exist, will look into the sky and see only darkness surrounding a single galaxy. The evidence for 2 trillion other galaxies will not merely be hidden. It will be physically erased from view by the expansion of space. The universe will have made itself unknowable. We live in a rare window. Right now, at this exact moment in cosmic history, the universe is still visible in its richness. We can see 2 trillion galaxies. We can measure their distances, study their structures, and reconstruct their histories. We have that knowledge. But knowledge and access are not the same thing. The universe has given us eyes that can reach across billions of light years, and legs that can barely cross the solar system. It lets us see almost everything and visit almost nothing. Andromeda hangs in the autumn sky tonight. The same faint silver blur that Al-Sufi recorded more than 1,000 years ago. It is beautiful, familiar, and close enough to photograph with a simple camera from a backyard tripod. And it is separated from us by 2.5 million light years of expanding, deepening, permanent void. It is the nearest major galaxy in the universe. It is as close as another galaxy gets. And it is so far away that the light you see tonight began its journey before your species existed. Nothing we will ever build will make that journey in return. The galaxy next door is not next door. It never was. On a clear autumn night, Andromeda can be seen without a telescope.